Hello, Physics 11, and welcome to your introductions to energy. So, to start out with, what I would like to do is try and find a definition for energy that may help us. So let's take a look here. One of the most common definitions given to energy is this: the ability to do work. In other words, if an object has energy, an object can do something. If we give an object potential energy by lifting it up, well, then it could gain some energy again by dropping it down. It could cause some effect or some change in the world. That's the idea of doing work. Now, when it comes to the definition of work, work is usually just described as a change or transfer of energy. So you can kind of see here that this is sort of a circular definition. Energy is the ability to do work, and work is just the change in energy. So it's not necessarily getting us that farther ahead in terms of trying to understand what energy really is. So a good way of dealing with that when you have these circular definitions that aren't really going anywhere or not really doing a lot to explain it is maybe in the form of an analogy. So a common analogy that's given with energy is comparing it to money. So there's a number of different ways that you can think about a comparison between these two. So if I set them up in a table like so, I've got energy and money as my analogy. Well, there's a couple of things you can think of. Now, throughout these lessons, it's a good idea for you to kind of pause for a moment here and there to try and think about some of these answers for yourself. So I'm going to give you if you want to just pause the video for a second, see if you can come up with some sort of analogy that compares these two. Okay, if you're just coming back from a pause, then here we go. So hopefully you've got some of your ideas already, but let's see some typical examples of comparisons. So one thing about energy is that energy can be stored, and we call this potential energy. And for money, money can also be stored, or it can be invested. So this is one way that energy and money are similar. Energy is conserved. And actually, I'm going to add something to that. I'm just going to say that it's conserved locally. So it is true that overall the total amount of energy in the universe is a constant as far as we know, but also the total amount of energy in a given system is conserved. So a system, for example, could be just a ball and the earth. I lift a ball up, I've added some potential energy into that system, and if I drop the ball, when the ball drops, it will gain a certain amount of kinetic energy, and the amount of energy gained in potential or lost in potential will be the same as the energy gained in kinetic, in that case, when you drop the ball. So it's conserved locally. Now I can add energy into a system, I can take energy out of a system, but in a given system with no external players involved, then it will be conserved. And likewise, money is also conserved in a local economy. So what I mean by that is if I go to a store and I give them $10, I'm down by $10 and the store is up by $10. Obviously, money is a bit more complicated in that sense than energy. However, in a local situation, the total amount of money is conserved. There's also different types. This is another way that these are similar. So there's different forms of energy. Just like there's different forms of money. You could have cash. You could have money stored electronically. You could have investments, etc., etc. So you have a lot of different ways that you can store money, just like there's a lot of different forms of energy. And maybe one thing to point out is cash kind of having money on you, this would be sort of equivalent to our idea of kinetic energy. So it's money that an object, or it's energy that an object has with it, just like cash is money that you have with you. So these two are kind of similar in that sense, that it's kinetic energy is the energy stored in an object, whereas for reasons I won't get into in too much detail, potential energy is usually, or is always, energy that's stored in some sort of a field. So it's stored energy in a field. Kinetic energy is the energy that's in an actual object itself. Okay, so within this unit, we are going to be concerned with two types of energy, as well as this idea of work done. So I'm going to give you the formulas right off the bat, and that way we have these to use throughout the next month or so of learning about energy. So the first formula we have is our formula for kinetic energy. And the formula for kinetic energy is 1/2 times the mass times the velocity of an object squared. So for example, if you have a baby and a horse running towards you, obviously if they're moving at the same speed, the horse is going to have more energy because it has more mass. Likewise, an object that's moving faster is also going to provide you more kinetic energy. And you'll note here that this is something that's squared. So in a sense, velocity has more of an impact. If I double the mass, I'm going to double the kinetic energy. Whereas if I double the velocity, I'm going to have 4 times the amount of energy because that quantity, velocity, is being squared. The next form of energy we have is potential gravitational energy. You can write it as EP or EPG, that's fine. And the formula for this is simply the mass of an object multiplied by the gravitational field strength, which we remember is 9.81, and we're going to multiply that by the height of an object. So, for example, if I have a heavier object, it's going to have more potential. If I were to move to a planet with higher value of g, let's say I moved to Jupiter, then g was higher than 9.81, that would give it more energy. Or if I move it to a higher height, it's also going to have more potential energy. And the last formula that we are going to use this unit is going to be this. So work is also equal to delta E, or the change in energy. And the formula for this is going to be the force that we apply, multiply by the distance, and multiply that by cos theta. Now, this part here, this cos theta, is only going to be relevant when there is an angle between the force that you're applying to an object and the distance, or the direction of the distance that it's moving. So if I apply a force in this direction and an object also moves in this direction, then the angle between that would be 0, and hopefully we know by now that cos of 0 degrees, cos of 0 degrees equals 1. So it's at its maximum. So if I am pushing an object to the right and the object is moving to the right, then we can just use force times distance. However, if I was applying a force in this direction to an object and the object was moving in this direction, then I would need to take into account the angle between those two vectors. But for now, we're going to try and keep it simple, and we'll try this cos theta maybe on some more challenging problems coming up. So, one of the nicest analogies or nicest ways of explaining how energy is conserved, like we said before, energy is conserved locally, so the amount of energy in a system is not going to change. So pause the video for a second and see if you can think about what are the energy changes when I take an object and I throw it upwards. So I've got, say, a ball in my hand and I'm going to throw it upwards. What are the initial forms of energy? What are the final forms of energy? What energy changes are taking place? So just pause the video for a second and see what you can come up with. Okay, so hopefully you're back from pausing it. And in this case here, when we throw an object up, let's say we're counting this point here as our height of 0 meters. Let's say it's the height above my hand when I release an object. Well, at that point, when I initially throw something up, I don't have any potential energy. So my potential energy is going to equal 0 because I'm saying it's 0 meters above my hand at that initial point where I'm just letting the object go. However, it does have some kinetic energy. So it has some kinetic energy initially, and then it doesn't have any potential energy. Now, as the ball moves up, it's going to finally reach the top of the height, and at this point here, at the point when the ball reaches the very top of the throw, if I'm throwing it straight upwards, it's going to stop moving. So we've seen that in kinematics. When you throw an object up, when it reaches the very top, there is no kinetic energy, or there's going to be no velocity. And likewise, if we have no velocity, then we're going to have the no kinetic energy. It's stopped moving at the top of the throw, but you will have potential energy. The object is now a lot higher than it was before. So in other words, we went from having kinetic energy to having potential energy in our system. And when the object is going to fall back down again, so now it's falling back down, and when it reaches the bottom here, at the last moment when it hits the ground or hits back to your hand, you're going to have no potential energy. The potential energy has now reached 0, but you will have kinetic energy right before it hits your hand. It's going to be moving quite quickly. So in total, for this whole scenario, you start out with potential energy, and then you move, you start out with kinetic energy, my mistake. Start out with kinetic energy, and that changes to potential energy at the top of the throw, and then as it falls back down, it changes back into kinetic energy. Now, a common way of describing this idea of energy, and also kind of it works to illustrate an important point about conservation of energy, is sometimes when an energy is initially taught, it'll be explained in terms of these buckets of energy. So I'm going to try and do that here to help make this a bit more clear. So this is my initial scenario here. So this is my initial energy, and this is going to be my final energy. And I'm just going to draw this for the first scenario, where it's going from your hand, moving upwards until it reaches the top. Now, at the beginning, we had 2 buckets of energy, and we're going to call this our kinetic energy bucket and our potential energy bucket. Now, in the beginning, we initially had some kinetic energy, but our potential energy bucket was 0. When we get to the top of the throw, we still have these 2 buckets of energy. However, like we said before, our kinetic energy bucket is going to be empty now. It's reached the top, the velocity reaches 0, and we know that when the velocity is 0, kinetic energy is going to be 0, and so we're going to have this much potential energy in the end. You can think about you're pouring energy from one bucket into another bucket. The total amount of energy, or the total amount of kind of this fluid that we're sort of imagining this as if we're thinking about buckets, it's going to it can't change unless there's some sort of outside force being involved, which is the work done, which we're going to get to in a couple of more classes, a couple of weeks. So this is just another analogy to kind of explain what's happening with the total amount of energy. It has to be remaining the same, however, it just changes from one form to the other. Okay, now let's take a look at this second half of the scenario. So this is where the ball is dropping from the top and falling back down to the ground again. So in this case, we've already discussed this. We started in this case here with kinetic energy, with potential energy when it was at the top, and that changed down to kinetic energy right before it reaches the bottom. So how could we calculate what the final velocity is? Well, we're going to use familiar notation. So this is notation that we've seen before, and hopefully we're used to it by now. This idea of using the sigma or summation notation. So because energy is conserved, whatever energy you have in the system at the very, very beginning is going to be equal to the sum of the energy that you have when at the end of the scenario. So at the beginning of the scenario, the ball was up at a high height and it had a certain amount of potential energy and no kinetic, and in the end, it had a certain amount of kinetic energy, but no potential energy. So this is using this sigma notation idea. So we've seen this before. Now in this particular problem, this might be a little bit of overkill, but again, if you get into good habits of always starting all of your problems in this way, then you're setting yourself up for success in the future. So let's think about what this really means. So we know that we have to figure out all the forms of energy that we have in the beginning. Okay, so we start with our initial forms of energy. We've already discussed this, so we know that our initial form of energy is going to be our potential energy, and that's going to equal our final form of energy, which is going to be our kinetic energy. Now what I'd like you to do is plug in these variables. So we know we have our formula for potential energy, we have our formula for kinetic energy. So if we put these two formulas into their respective places on the formula, just take a minute, pause the video, and find your value for velocity. So not necessarily a numerical value, but find out what is going to be our formula for v in this question here. Okay, take a second and pause the video, try this out for yourself. All right, if you're just coming back, then your potential energy formula we know is m times g times h. This is going to equal 1/2 times m times v squared. Now, you may have noticed right off the bat that we have m's in both of our formulas, and these are going to cancel out. And when we're not dealing with work, if we're ever just dealing with potential energy and kinetic energy, this is pretty much always going to be the case, that the mass of an object isn't going to impact its total final velocity. And we can kind of think back to Galileo's experiment where he's dropping two objects and they fall to the earth with the same speed. This is another sort of proof of that here. We can see that the mass of the two objects won't make any difference. If I lift something up from a certain height, it's always going to drop with a certain velocity. So this is another way of proving that point. Now, if we rearrange this formula, what we're going to do is we're going to multiply both sides by 2 to cancel out this. And then we're going to have to take the square root. So we're going to be left here with v squared equals 2gh. And so therefore, if we take the square root of both sides, we're going to have v equals the square root of 2 times g times h. Now, this is our formula. Again, mass is not in this formula. It doesn't matter. If you lift an object by a certain amount of height, h, and you drop it on a planet with a constant value of g, then you can always calculate what your v is going to be. Okay, so let's take a look at a more complicated problem. So I'm going to ask you to pause the video again one more time. So taking a look at this, before you pause, take a look at this scenario here. We've got 2 or 4 different slides. All of the slides are 4 meters tall, but they all have different shapes. And so if you were to put a child on each of these slides or each of these ramps at the same height, the initial height of 4 meters, which would be the largest to smallest speed at the bottom? So I'll ask you to pause. Don't think about this too long. If you've got the answer, that's great. If you're thinking about it too long, then just unpause the video and come back. Okay, if you're back, then hopefully you have come to the conclusion that they are all the same. So the shape of this ramp didn't matter. Now, why is that? So if you got that, hopefully you did, then you're going to realize we're talking about a physics principle that we've already mentioned in this case here. And that is that energy is conserved. Now, this is one of the really nice things about dealing with energy. If we were dealing with kinematics, this problem would have been very, very difficult to solve. You could have solved for the first A and B, but really without some pretty advanced calculus, you wouldn't have been able to solve C or D. So it would have been an impossible question to ask a grade 11 student if we were dealing with kinematics. And even between these two, it would be a very difficult problem to prove that they would have the same speed. This is the brilliance of using energy to solve problems. When you're using energy, then all you need to worry about, all you care about, is the initial and final conditions. So you don't need to worry at all about what's happening in between. You don't care about any of this part of the journey. So you've got this person sliding down, having a good time, they're sliding down the ramp. You don't care about anything that's happening between here and here. We know in this case here, they will obviously accelerate quicker. In this case here, they're going to accelerate with a slower rate, but they'll be accelerating over a longer period of time. So we can do all the calculations to solve for that. However, at the end of the day, because we're using energy, all we care about is that at the beginning, there was this much energy. At the end, there's going to be this much energy, and those two values would be the same. And so just like in our question that we solved up here, if we know that initially it had mgh, and at the end it had 1/2 mv squared, well, guess what the velocity is going to be? The velocity is going to be the square root of 2 times g times h. And in this case, because we know that it starts at 4 meters, this is going to be the square root of 2 times 9.8 times 4, and we can calculate that. So whatever value that turns out to be, that's going to be our value of the final velocity. And it doesn't matter if you go down slide A, slide B, slide C, or slide D. All we care about is the initial and final conditions. They all started out with m times 9.8 times the height of the slide, which is 4, and they all end up with the velocity equaling the square root of 2 times 9.8 times 4. They're all going to be the exact same value of the velocity in the end, regardless of what happened in the middle. So this is one of the ways that energy makes some fairly difficult problems from our last unit actually fairly straightforward to solve. So hopefully you consider that good news, especially as we start out our quarantining learning as it is right now. Okay, so the last question I have for you in terms of our lesson is this one here. So example 4, a boy gets a running start down a hill and jumps on his toboggan at a speed of 3 meters per second. The mass of the boy and the toboggan together is 40 kilograms. The hill is 6 meters high and the length of the slope is 10 meters. So what is going to be the boy's final velocity? Now, you may be tempted, in this case here, always a good idea, following our disk method, is to do a drawing. So in this case here, this is saying that the hill is 6 meters high, the length of the slope is 10 meters, and we're trying to find out what is the final velocity. So V final, this is our main question we're trying to address here. So I'm going to ask you to kind of pause the video as we go. So I'm going to work through the solution, but I would love for you to try and do as much as you can independently. So if you're stuck, feel free to unpause, see what the next step is going to be, and then try pausing it and seeing where you can carry on from there. In this way, you're sort of doing the work independently to the extent that is possible. So please give this a try. Okay, if you're still stuck, let's add this reminder here. We're always going to start with this principle, that the sum of our initial energy is going to equal the sum of our final energy. Now, the first step we need to figure out here is, what are these forms of energy? So we know that the boy gets a running start, and he's moving at 3 meters per second. So this is at the very beginning. Before he jumps on his toboggan, he's already moving at 3 meters per second. So what is one form of energy that he has? Well, he's going to have some initial kinetic energy. We also know that he's at the top of a 6 meter tall ramp, And so because he's at a 6-meter tall ramp, at the top of a 6-meter high ramp, we also know that he's going to have potential energy at the start. Now if we think back to our bucket analogy, we're going to have this. So this is the energy initial, and this is the energy final. In this case here, there is a bucket with some potential energy, and there's also a bucket with a little bit of kinetic energy. Now, in the end, what form of energy do they have? Well, now they're at the bottom of the ramp, so they're not going to have potential energy. All that they're going to have at the end is some kinetic energy. So if we look at the final scenario here for these two buckets of energy, we're going to have nothing at all in our potential energy bucket, but all of the energy that we had from our potential plus the energy that we had from our kinetic initial is all going to be in the kinetic energy bucket. So this should be final as well. This is what we're going to be left with in terms of our energy. So we had some potential at the beginning, some kinetic at the beginning. In the end, all of that energy is now in the form of kinetic energy. So just giving this analogy. Okay, if you're working and making progress, you can pause now. If you are just coming back, what we would need to do now is break these down into their formulas. So we know, in terms of our higher level thinking, we know that our initial and final energy is going to be the same. We identify the form, so initially there was kinetic and there was potential. In the end, there was just kinetic. Now we break these down, so we have 1/2 mv squared plus mgh. Initial is going to equal 1/2 mv final squared. If you want to, you don't have to, you can certainly plug those values in, but you can also cross out the m's. They're in all the terms. So what I'm going to do next is I'm going to multiply everything by 2. This is going to cancel out our 1/2 over here. So now we're left, if we rearrange this, we have v final squared is going to equal 2gh plus v initial squared. And if we plug in our values over here, we're going to have v final squared equals 2 times 9.8 times 6 plus 3 meters per second squared. So this is going to equal, let me get my calculator, 2 times 9.8 times 6 is 117.6 plus 3 squared, which is 9. So v squared will be 126.6, and therefore v is the square root of that. And so v is going to be 11.3, or to 2 sig figs. Really, it should be 1 sig fig, I guess, with the question. But let's go with 2 sig figs. We'll just round this to 11 meters per second. So I didn't, you might have noticed, I didn't use this value at all. The 10 meters, again, was irrelevant. It was just there to kind of trick you. Similarly to the question above, you don't need to know what's happening throughout the slide. You certainly could calculate that. You certainly could do your kinematics from before. All that information would be fine for you to use. We've done forces on an inclined plane, and now you just realize that that was not necessary in all the cases. So in this case here, we can ignore that. Again, all we needed was our initial conditions, kinetic and potential, and our final conditions, kinetic, and we solve for that. So I hope you've enjoyed this video. Hopefully it's been educational for you. Again, the homework that I'd like for you to try and solve is try and solve at least questions 1 to 5b. Those are going to be a bit more straightforward. And if you feel up for it, again, I know that this is a weird form of learning for you. If you're able to do 5a and b, I'd be happy with that. If you're not able to for any reason, let me know or send me an email, and I'm obviously more than happy to help. And again, still holding fast on the news if I'm allowed to do the live stream on YouTube. We'll find out if that's allowed, and carrying on from there, hopefully that'll be an option that we have to give you a little bit more kind of hands-on, one-on-one help. And if you are feeling up for the challenge, please go ahead and try numbers 6 to 11. Okay, talk to you next week.